So now we talk about some ways of assessing and comparing probability distributions. One of the most fundamental ways to kind of look at probabilities a little bit differently is to look at their entropy. So entropy is a term that'll come up if you're a physics person, you'd know it and use it a lot. In our case, it means essentially uncertainty, right? So as entropy increases, the noise of a system increases. It comes up a lot in signal processing, obviously. So you talk about the entropy of a signal, which is how much noise there is in it, how random it is, and the higher the entropy, the more random it is, the higher the uncertainty. It also means usually the lower the probabilities of any kind of particular events occurring. If all events are equally likely to occur, then your entropy is maximized, right? And so the way, so that's it's got a whole field in signal processing and in information theory about what entropy means. When we're talking about it just in terms of probability and data, if data has higher entropy or models loss or performance measured as entropy is high, that means it's not doing very well. That means there's no pattern there. High entropy is good in encryption. You want to hide everything. Complete static, that's completely meaningless, has maximum entropy. And a very deterministic system has low entropy. Usually we're trying to build models that have high probability confidence about events. So we want to predict things with a certain probability. So we want to lower entropy. So I was usually trying to drop that. The way you compute entropy is you take the probability of some events and you multiply the probability by the log of the probability. We're computer people, so our logs are always base 2. I guess it doesn't really matter in terms of how you're defining it, unless your x's are binary numbers. So you sum over all the events and sum them together. So you're weighting the probability of the event by this this log of the probability, and then taking the negative of that. So another way of seeing this essentially as the surprise of seeing some observations. If your entropy is high, but then an event occurs that has high entropy, then it isn't as expected because there's more noise and you wouldn't have predicted that. And in the sense of information, it kind of tells you how much information is being represented in a distribution. Because like we said, if you have a uniform distribution where every variable has the same probability, then your entropy is going to be high and you can't tell anything about the different variables or events, right? So there's essentially no information in there, right? Whereas a distribution that has lots of specific components to it has more information, right? It's telling you that this thing is different than this thing. You can do all kinds of comparisons. But a uniform distribution doesn't tell you anything, and it has very high entropy. So if we talk about the entropy at h of a random variable x, and then we range its value from 0 to 1. In this case, we're doing a Bernoulli random variable, so this is the probability of a coin flip, right? And so if the coin is fair, and it's just a normal coin that flips heads 50% of the time and tails 50% of the time, that gives you the maximum entropy in this particular case because you don't get that much information from every event, right? So adding up the probabilities of things takes you a longer time to work it out. But if if it's a very unfair coin and comes up heads 9 times out of 10, then it's going to be on one side here, and it would have lower entropy because you can work out the probability more quickly. That's kind of a way to see it. So in terms of probabilities and distributions, something that we'll very often want to do is talk about whether these distributions are similar to each other. So at one point in the course, if you haven't got there yet, we'll be talking about distances between sets of data points, right? So is this cluster of points similar to this cluster or not? And that could be done by comparing, the XY positions or the features of them and doing all various kinds of comparisons. But what does the distance between two distributions look like, right? So we have two distributions or two random variables, x and y. We know it has a certain structure, and this is just a one-dimensional version. It could be many dimensions, but it has higher and low probabilities, and these all sum up. The probability sum to 1 because they have that property. But how can you talk about the distance between these, right? That's a question to think about. What does it mean for two distributions to be near each other or far from each other, right? Does it mean that they give the same probability in all possible events? Or does it mean that, like, if you just shifted the average or the mean center of it to one side, that they'd line up? There's various ways you could think about two distributions being similar. Maybe you flip one and it gets become identical, but then it's almost like an inverse of it, right? So a very common way to do comparison of two probability distributions is the KL divergence, Kullback-Leibler divergence. It also can be seen as the relative entropy, because you are essentially using that entropy calculation on one of the probabilities distributions, but then you're normalizing it by the other one. So you're saying, what's the, in this case here, P and Q are both full probability distributions, right? So you could give P a value of X and it would give you an actual probability at every case, and Q as well, but you don't know anything about how they're related. They could be completely unrelated. And you can use this KL divergence to say, well, here's how at least similar they are to each other, or how close they are. So you sum over all the data points, or some sampling of the data points. If they're continuous, you'd have to pick a set of sample points and compute this, or compute the integral over it if you have a closed form for the probability distribution. And it's the entropy normalized within the log of the other one. And so if it's 0, then that means the distributions are equivalent. So it has that nice property that if they are identical distributions, this distance will come out to be 0. And so this divergence will become out to be 0. But when the numbers get bigger, and you don't necessarily know exactly what it means. But it does have this information interpretation that essentially you're saying, well, if Q is the true distribution, and you're using P as your approximation, then how much information are you losing, right? How often would you get things wrong if you're doing betting, or how incorrect would you get things? How much less information is being stored? So maybe P is a smoother version, or something that's very parametric and easy to understand. It's a bunch of Gaussians or something you can write down, and Q is like reality and you don't know what it is. And so you're talking about what this distance is. An interesting property of this is that it's not reversible. So KL divergence of P to Q is not usually the same as Q to P. You can require that they are, and so you do the double KL divergence, and you basically combine and average the distances from both directions. But that would just be a different similarity metric to use. Another way to compare two distributions is the mutual information. And so you have, in this case, a joint distribution between two variables x and y, and you're factoring them to be, so when we factor them this way, right, remember what that means? We're assuming that they are independent, right? That they can be described as independent distributions. And so you talk about what's the ratio of the joint divided by their independent. So how much, essentially measuring what's the ratio of their dependence to their independence, right, as a probability, and then turning that into an entropy calculation. So how much uncertainty is represented by the assumption that they are independent or not, right? This always gives you a positive number, which is great. So it kind of behave almost like a probability. If they're actually independent, it will give you 0, right? Because this would be equivalent, right? If no, not, I don't need my double if here anymore. If x is independent of y, right, then that means that these things are actually equivalent to each other, right? So this would just give you 1 and log 1 of 0, and the whole thing gives you 0. So you know that it will be 0 for them being independent, and the more dependent they are, the higher the mutual information will be, and that's why they call it the mutual information. It's kind of a measure of how much information or overlap is there between these two. Right? So KL gives you how different they are, and if they're identical, you get 0. This one tells you how much do they share. So it's a measure of similarity, but just done in a different way. And you could also think of it that is actually the KL divergence between the joint distribution and the independent distribution. Another way to recast this in terms of entropy is to talk about the entropy as this joint thing. So remember, we had the joint probability of x and y can be treated as the sum of the probabilities minus their overlap. Mutual information is like the entropy form of that. So you can add the entropies and subtract their overlap, and you get the mutual information. You could also then normalize your mutual information by the entropy so that it behaves much more in scale to the size of the distribution. Similarly, information gain, which we'll use a bit in decision trees, uses the entropy in a different way and kind of takes the entropy of one variable y given x and subtracts it from the kind of independent entropy of just that variable y. So you're kind of taking out how much x contributes to things here. So knowing the values of the distribution of x, does it change the entropy by very much? And if it's not very much, then maybe that variable is not particularly useful. So when you're trying to decide which dimension or feature or variable to split on or build a more dedicated model on, information gain is something that could help you decide, like, is x worth it? Right, because you're looking at this notion of how much information it helps add to your model. Because it could be that adding one more variable adds huge computational complexity, makes your model run 10% slower or something. Hopefully not that bad, but some proportion, because your model is getting bigger. And if it only gives you a very small percentage improvement in your ability to distinguish whatever your model is doing, may not be worth it. So, but these are things where we're talking about assessing an entire probability distribution for some particular purpose. And once we're looking at specific algorithms for classification or anything else, you could kind of see this in more context. So another concept that I'm kind of using implicitly in some of these descriptions is the idea of a random variable. So we have this probability P of taking on a particular value, probability P of x, where x takes on a particular value, so the dice that's going to take on one of the numbers in it. We're talking about the probability distribution of that dice, so that's kind of a very simple version, but a random variable really could be any function from this omega to the reals, to the probabilities. that is useful to us, right? So it could be the a variable x, which is the probability of rolling of 10 rolls in a row on a dice, or the probability of, the example I'm talking about of stocks passing above a certain level. That's a random variable, because you're saying there's a bunch of actual events that could occur, and I'm going to say all the possible events that could occur, like the way that my stock A could go above a certain level today, go up by 100 points, I said. That's a random variable because it could go up by 50 points, 90 points, 112 points, 170 points, 1,000 points, right? All of those are outcomes that are possible. And so the probability distribution is over every one of those events. And the set of events where it satisfies my rule, which is it's more than 100 points, it contains many different values, right? So I'm kind of dividing the world into two classes. All the events that where that stock had less than 100-point raise, and all the events where it had more than 100-point raise. So my random variable is the function that does that. And then I say, well, how likely is each of the outcomes, right? So in that case, I've got a binary random variable that says it's either above or below 100 from today's growth. But in order to get there, I have to count many different things that could happen, right? So that's what a random variable is. It's really a function that lets you specify something that you want to make a prediction about or learn about. So here, this page I'm looking at here is the web page where we've got more of the notes. It's from a previous course where we use some of the same ideas. I'll share it up onto Learn so everyone can see it and find it more easily. It's got a bit more detailed notes on probabilities than I'm going to talk about here, but you can read through it and read other places as well, of course, and then come ask us on Piazza and work things out if there's anything that isn't quite clear. And don't worry about every possible thing on this page at the beginning, because some of them you may not end up using very much, but when it gets mentioned, it's useful to come back and say, what is a cumulative distribution or a mass function? And it's really all different ways of combining things we've talked about, right? So a cumulative probability distribution, a cumulative distribution function, can be seen as a random variable where we say, well, what's the probability of all the events happening up to a certain value, right? So I'm essentially talking about that when I'm talking about my stock value. I only care about the probabilities of events beyond 100, right? But really, there's a probability of every number happening today that the stock can go anywhere from minus its value to positive infinity, technically. They all have different probabilities, and the probabilities around infinity and zero are incredibly low or zero. But the probability of my variable of that stock being above 100 is an area in that curve, right? And so you could have a cumulative probability function where you only always care about the probability of everything up until that point, right? So what did I want to get to here? The other part,